Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Before I introduce this week's guest, here's a quick reminder about the upcoming TWiML online meetup, which will be held tomorrow, September 12th at 3 o'clock Pacific time. The discussion will be led by Nikola Kucherova, who will be presenting Learning Long-Term Dependencies with Gradient Descent is Difficult by Yoshua Bengio and Company. Of course, it's best if you've taken a look at the paper in advance, but even if not, you're sure to learn something from the discussion. For more information or to register, visit twimlai.com/meetup. See you online tomorrow. If there's any one topic that I've received a bunch of requests about covering on the show, it's the subject of this week's discussion, Evolutionary Algorithms in Machine Learning. My guest this week is Risto Miikkulainen, Professor of Computer Science at UT Austin and Vice President of Research at Sentient Technologies. During our talk, Risto and I discuss some of the things Sentient is working on in the financial services and retail fields, and we dig into the technology behind them, evolutionary algorithms, which is also the focus of his research at University of Texas. I really enjoyed this week's interview and learned a ton, and I'm sure you will too. Before we get to the show, a word about this week's sponsor, Cloudera. You probably think of Cloudera primarily as the Hadoop company, and you're not wrong for that. But did you know that they also offer software for data science and deep learning? The idea here is pretty simple. If you work for a large enterprise, you probably already have Hadoop in place, and your Hadoop cluster is filled with lots of data that you want to use in building your models. But you still need to easily access that data, process it using the latest open source tools, and harness bursts of compute power to train your models. This is where Cloudera's Data Science Workbench comes in. With the Data Science Workbench, Cloudera can help you get up and running with deep learning without massive new investments by implementing an on-demand, self-service deep learning platform on your existing CDH cluster. To learn more about the Data Science Workbench, visit twimlai.com/Cloudera. And for a limited time, Cloudera is offering a free drone to qualified participants who register for a demo. Again, the URL for that is twimlai.com/Cloudera. And now, on to the show. All right, everyone. I am on the line with Risto Miikkulainen, who is Vice President of Research at Sentient Technologies and a Professor of Computer Science at University of Texas at Austin. Risto and I recently tried to connect at the O'Reilly AI conference in New York. Unfortunately, we weren't able to do an in-person interview, but we were able to get on the line together. And I'm really looking forward to this conversation, and I think you'll really enjoy it because we'll be talking about something we haven't talked about yet on the podcast, and that is evolutionary algorithms. So, Risto, welcome to the podcast.
Thank you. Pleased to be here.
It's great to have you on. Why don't we get started by having you tell us a little bit about your background?
Okay. Yes. So I got my PhD at UCLA 1990 and was working at the time on neural networks, which I've continued doing all my career, but got also interested in evolutionary algorithms about the same time and have gradually drifted more in that direction, and especially in the intersection of those two things. So we've been evolving neural networks since the early 90s, and you can view that as one way of training neural networks in domains where you cannot really do other types of learning like deep learning, supervised learning. So that's been my research focus. Originally I did a lot of work in natural language processing with neural networks and then understanding the visual cortex with neural networks. Most recently, this evolution-based work is focused on building robotic control, game characters, and more recently solving problems in the real world using this technology. And that's what I'm doing at Sentient. I'm on leave from UT Austin, have been for 2 years, trying to take the technology to the real world. And it's been a lot of fun.
So tell us a little bit about what Sentient does and what the focus is there.
Sure. Sentient has been around actually for 10 years, although we came out of stealth only 3 years ago or 2 years ago.
That's a long time in stealth.
Well, it took a while to develop all the infrastructure. So initially, Sentient was doing stock trading and still is doing stock trading as one of the applications. It's a great first application because you don't need to have much customer support and other things like that. You just run your algorithms and they trade directly and make money. But it took a long time to build those algorithms and also build the infrastructure, the computing infrastructure. So Evolution is one of those technologies that requires a lot of computing power to excel. And here at Sentient, we built that kind of a computing power, a distributed system across the internet using, at that time, 2 million CPUs to evolve stock traders. And that was very successful, and it was a lot of fun to build that. That was the first product, and then we changed the course, or added another direction rather, going to e-commerce, building intelligent interfaces to e-commerce. So there are 2 products there. One of them is Sentient Aware, which is a visual interface to catalog of products that understands what the user wants. It's more like a personalized assistant that you might find in Nordstrom or other fancy department store. You click on choices and the system will understand what it is that you're looking for. In a couple of clicks will get you what you want. The other one is Ascent, Sentient Ascent, which is a way of using evolutionary computation to design web interfaces so that they are most effective. For instance, optimizing conversion rate on an e-commerce website is one of the applications of that technology. So those are the 3 products. But behind all that, we are a technology company, so we develop evolutionary computation methods, deep learning methods, combinations of those, as well as surrogate optimization and backpack optimization in various domains. So that's our technology pace.
Okay. Actually, I'll get back to that. You mentioned 2 million CPU cores. Is that via the cloud? Is that distributed? Are those in your own data centers?
Yeah, that's interesting. This is like a grid machine, sort of like Folded or SETI at home. Yes, exactly. Same idea, utilizing freely available compute time. I mean, not freely available, we pay for it, but available idle compute time around the world. And this is, I think, a really interesting proposition. And there's so much compute distributed now in people's laptops, PCs, cell phones. And if we could harness that, we could do a lot of computing. But of course, things changed. The CPUs were perfectly good in the first several years when we were evolving stock traders. More recently, we evolved deep learning neural networks. And the need is a little different because they are trained on GPUs. So now we have to have access to GPUs, and the demographics has changed a bit. And this is a very rapidly changing space. It's also become very economical to buy a bunch of GPUs, thousands of them perhaps, and build your own center. So we are continuously looking for opportunities to harness computation, whatever form it is. But we have expertise in both kinds of setups.
Okay. And so is the company still using this highly distributed grid-like infrastructure, or have you shifted to an owned infrastructure?
Yeah, we are still using it, and we are also exploring other ways of getting the computation. They serve a little bit different purposes. One of them is very massively parallel and not necessarily that reliable, and that's good for some applications. And in others, you need more reliability. The compute has to be accessible all the time, and it has to finish. And therefore, you need different kinds of sources for compute, and we are pursuing several sources as a result.
Can you give us examples of the kinds of applications that work well and for each?
Yeah, so for instance, stock trading is very robust because we are evolving traders. And evolution in general, evolutionary computation in general is robust because you have a population of solutions and you are testing that population in a distributed fashion across the different compute sites. And if something goes wrong and you don't get back an evaluation of one of your candidates, that's okay. You have hundreds of other candidates. It's okay to lose one candidate or have it only be partially evaluated because there's a lot of noise in this evolutionary search process, and it actually thrives on diversity and multiple alternatives. So it's not dependent on any single alternative or an accurate evaluation. It's based on evaluating a lot of candidates and many times. and that you can do on a compute source that's very unreliable. Now, if you are building a particular application based on, say, deep learning, you want that deep learning network to be very well built and very well trained and reliable. And sometimes that training will take several days. So it has to be a reliable source so that you can get back that result of the training. Otherwise, you waste a lot of time on it. So that's where we need more reliable sources.
Okay. And so is the company still working on financial services, or did you migrate or pivot from financial services to the e-commerce solution?
No, we're definitely working on trading as well. It's more like an AI-based hedge fund than financial services. And there we have expanded to different markets. So that part is growing, and the algorithms have also evolved to some degree, but the base is still to run a hedge fund using AI. So the traders are automatic. They actually are looking at the stock market and deciding what the trends are and what should be done, and then to make those trades. Of course, there's a person also watching this with a hand on a red button in case something goes wrong. But that almost never happens. I don't think it actually has happened in that urgency. But sometimes also the stock market is interesting, that there might be something happening in a stock market. You can tell that now this is not a usual situation. It's going haywire, and we'll stop the trading and let it come back and become more normal. So there's a human in the loop, but it is interesting that AI can do much of this on its own.
And are you trading your own book, or are you working with other hedge funds and helping them trade?
Yeah, currently trading our own funds, and there's a plan to open it up in the future for investors.
Interesting. I wonder why, if you've got that working, it's kind of this perpetual money machine, right? Why even bother with retail?
That's a good question. Well, in the AI world and in the startup world and in the Silicon Valley, it's always grow, scale, get more. And this is a successful technology. So now the question is, what else can you do with it? And indeed, it's nice to have several different technologies and bases, and especially then because you start getting cross-pollination of them. So the second one we looked at was very different from evolutionary algorithms, was deep learning. And we found that we could use it to encode human preferences, what humans perceive as similar, and visually, and identified that this would be something that the retail industry could really use, because retail is changing rapidly and fundamentally. From the brick and mortar stores, we are changing into internet-based commerce. And this is a really big change, but internet commerce is quite clunky still today. It's hard to find what you want in those web interfaces. And the reason that was pretty obvious was that you have to know what you're looking for, and you have to know the keywords for those items that you're looking for.
Right.
And if you do, you may be able to find to your satisfactory some product that you're interested in. But if you don't, it can be very frustrating. And as a matter of fact, we've done some tests on that. Typically, in an e-commerce site, in a week, 15% of the catalog is actually seen by the users, because they have to go through these rigid categories and keywords, and it's very hard to find different variability or diversity in a catalog. We identified very early on that this is actually something that could be done differently. We could use human-like perception of similarity, visual similarity. So if we're thinking of, say, a catalog of shoes or jackets or sunglasses, then a human can identify something that he likes or he or she likes very quickly by being presented a bunch of alternatives. This is the one I like the most. And then another set of candidates comes up. And these are now based on the first click. They are similar to the first click, but variation around that area. And now you can click again. And it turns out in about 7 clicks, you can find anything in the catalog, according to our evaluation. And in that process, the users actually see about 70% of the catalog each week. And this is a situation where everybody wins. As a user, you have access to more variety, and the e-commerce vendor will sell more catalog, and the manufacturers get their products out there for people to see. So it is just fundamentally a better way to access e-commerce catalogs. And it's based on understanding human perception and training machines, training neural networks to represent those similarities.
That sounds like a really interesting application. So actually, you said the financial services, you started with applying evolutionary algorithms, and with this e-commerce application, the focus is more on deep learning.
Exactly.
Is that the right way to think about it?
Yes, that's exactly right.
Maybe let's dive into evolutionary algorithms now. Tell us, what you gave us a little bit of a taste of it earlier, but what does that mean?
All right. So evolution, and you can see this as form of, or similar to reinforcement learning, where you do not get the correct answer to learn from. I mean, in deep learning and most of the machine learning applications that are out there are based on these large data sets where somebody has collected the data. This is a situation and this is the right categorization or action at that situation. For instance, images and their classification, categorization, or speech and a transcription of the speech. And this is very doable. And we have systems that have come up, Mechanical Turk and Mighty AI and others who are now collecting and forming such data sets. And then systems like deep learning can be invoked to build models of those kinds of tasks. And it's very powerful. But there's a lot of tasks in the world where those actual correct answers are not known. So, for instance, driving a car, a mobile robot navigating, playing any kind of game, you don't know what the actual optimal answers are. And in such domains, the learning is based on exploration. You try out things and see how well they work. In a big picture, this might be called reinforcement learning. You get reinforcement to your actions. Now, reinforcement learning, actually, as a term, refers to a category or class of algorithms that is a little different from evolution in sort of social or a traditional sense. They are mostly, those reinforcement learning algorithms are mostly based on value function approaches, where you list all your actions and learn how good each action is in each state. And that's a different approach to solving a problem when you don't have gradients, when you don't have supervised targets. Evolution is a different approach. The idea there is that you have a whole population of solutions and you evaluate each solution. And as in biology, those who evaluate well get to reproduce more and generate offspring. And the offspring is somehow generated in various ways from the parents. You take an encoding of the parent, an encoding of another parent, and then you cross them over, just like in biology. So there's some kind of a linear encoding as like DNA, and you can take part of that DNA from one parent and another part from another parent to form an offspring. And that means that you are combining properties of both parents into the offspring. And this is the fundamental idea of the evolutionary search. You're trying to recombine components or schemas or building blocks, they are sometimes called, to find better combinations of them. And there's another component which is important as well, that's mutation.
Before you dive into that, I have a question about something you said about reinforcement learning. And that is, you said that the reinforcement learning is characterized by these value functions, and in order to evaluate these value functions, we apply gradient-based approaches. And you said that in order to do that, we can only do that under supervision of some sort. And elaborate on that, because we're typically applying, as you said, reinforcement learning in what we think of unsupervised problems.
Right. So supervised learning is different from reinforcement learning. So that supervised learning means that we do have correct answers and we can calculate gradients. In reinforcement learning, we don't have those gradients. We don't have correct targets. So it's based on exploration. So in reinforcement learning, the agent will try out different actions and will eventually get an evaluation of how well those actions worked out. And then dynamic programming is incremental dynamic programming is typically used then to propagate that reward back to the earlier actions and changing their value in this representation of how good each action is. So it is not supervised. Things get a little confusing because this, in its purest form, this kind of value function learning applies to a table of actions in a table of states. But that is very limiting. So we need to be able to approximate a large number of actions and a large number of states. And that means that a lot of times we use a function approximator and then use gradient descent to build that function approximator using the propagated values as targets. So we use gradient descent as a way of generalizing reinforcement learning, but the information for reinforcement learning comes from the outcomes of these exploration episodes.
Right, right. And one of the challenges with reinforcement learning is that you are, it's the right way to articulate this, you're kind of weighing exploration and exploitation, and your exploration tends to be focused around fixed paths, and you don't really have a built-in mechanism to combine different exploratory directions. And that sounds like that's one of the advantages of evolutionary algorithms.
Yes, this is absolutely right. So there are two main challenges for reinforcement learning. One of them is this large search space. Like I said, it works really well if you have a smaller space where you can enumerate all your actions and states. And it's difficult when those grow and become maybe continuous. And another problem is that it works well when your state contains all the information from the past. It's uniquely specified, or exactly specified. If you have partially observable states, then it becomes very difficult to learn using this kind of value function approach. And both of those are actually addressed if you use evolution to construct neural networks in such tasks. So neural networks work very well when they are in continuous domains. You don't have to enumerate all the possibilities. They are already doing the function approximation. And, regarding the second problem, you can evolve recurrent neural networks. And when you have recurrency, your entire sequence of actions that you've taken up to this state is taken into account in making the next decision. And therefore, it can disambiguate much of the state ambiguity and therefore work better in partially observable problems as well. So that is true. You have to have a decision-making system such as a neural network as a base, but then you can evolve that neural network in order to get over these two challenges to reinforcement learning.
One challenge to reinforcement learning is the issue of reward attribution. Is that covered under the partially observable state issue, or is that a separate category of challenge? And how is that addressed by evolutionary algorithms?
Well, they are related. And so reward attribution, if you have a partially observable problem and you make a decision, part of the credit for that success for that decision depends on how you got to that state, those unobserved variables. So if you have a system that takes into account all the actions that got you to that state, you are doing the credit assignment better and more accurately. So yeah, in that sense, they are related.
Okay. So maybe, is there a way to, granted that a podcast is limited in its bandwidth, not having a visual component here, but is there a way to kind of walk us through the setup for an evolutionary algorithm and how it's applied to training neural networks?
Sure, and I've been vigorously waving my hands here, but you haven't been able to see it all along. But so, yeah, the big starting point that's different from reinforcement learning is the population. So you have a collection of individuals, and typically it's 100, 200 maybe. In some cases, in different variations, might be smaller.
And so what is an individual?
Each of the individuals represents a solution, a potential solution to the problem. Like in this case, in the simplest case, it could be a neural network. And it means all the weights and all the nodes, weight values and all the nodes and the structure of the neural network.
Okay, so it's pre-constrained by architecture. You've defined an architecture for this target neural network, and you're using the evolutionary algorithm to figure out its various parameters as opposed to evolve the network architecture itself.
Well, that's the simplest way of doing it. But the most powerful evolutionary neural network systems actually evolve the architecture as well.
Oh, really?
You just have to have a representation that can be encoded into a string typically, or a tree, but most often a string, like DNA. So you have a DNA representation of that solution, and it may include the weights on the connections. It may include the hyperparameters, like the slope of the sigmoid or something like that. And it may include the topology, like how the graph is actually connected between nodes. It's just an issue of how you encode it. But the end result is that you will have some kind of a string representation or a tree in a more general sense. for each of the individuals, for each of the neural network, the solutions. And now you have a population of them. And then on that population, you run an evolutionary algorithm. And there are many flavors of those. What I've been talking about is the genetic algorithm flavor, John Holland's tradition. There are many others too. But that is the most closely associated with biology, in that you take each individual, you test them in a task, you evaluate them in a task. And that's where the parallel computing comes in, because you have a population, you can send each individual to a different machine across the internet to be evaluated. And sometimes, most of the time, the evaluation is the most computationally expensive part of the algorithm, because you may be driving a robot, or you may be doing stock trading, or whatever it is that you're doing. It takes time to evaluate. And that's really nice, because evolutionary algorithms parallelize very well in that sense. Each individual can be evaluated separately. And then you get back their values, their fitness values, how well they perform in the task. And now the entire population is associated, each one individual is associated with a fitness value. And you can find the best ones, and you can find the worst ones. The worst ones you throw away, and the best ones you pair up so that you can do crossover, as I mentioned earlier. And also the second component of evolution, the mutation. Crossover gives you new combinations of building blocks or schemas, partial solutions. Mutation creates new ones, because it's not necessarily, you usually initialize the population randomly, like random weight neural networks, but it doesn't guarantee that you have the weight in the right place when you need it. So mutation is a mechanism for creating that. It's a random change in the weight value, a random change in the topology that happens on a low probability, about 2% or 4% or so, as part of that evolutionary step. So you've taken your parents and you created their offspring, and that offspring then is used to replace those poor individuals that were thrown away. And that creates your new population, a new generation. And then this process repeats. In this process, in essence, you are doing a parallel search in the solution space. Starting from your 100 initially random individuals, you gradually reward those that perform the best, and you perform more search in the areas where there's better solutions. But it's in parallel, so you're still not following just one potential kind of solution, but you are in parallel focusing on multiple potentially good solutions. And eventually, then you find some really good ones, and the algorithm focuses on refining that area and finding the absolute best in a smaller area around the best solution. That's what ends up happening. And that's evolutionary algorithm in a nutshell. As I said, there are many variations, and they're also interesting to talk about. But that principle of parallel search in a solution space, which is directed by these periodic evaluations in the real world, is the essence of the method.
Okay. So it sounds like, maybe perhaps not if applied to a deep neural network, but if applied to a more simple type of machine learning model, essentially what we're doing is a search of the solution space that, could be analogous to a grid search of hyperparameters. But in the evolutionary world, we're able to constrain our search and as well as parallelize it. And so I'm imagining that, from like a big O perspective, this is, log n time as opposed to n or something like that with a grid search. Am I thinking about that the right way?
Yeah, that's intuitively, I think that's correct. It's, of course, a different question of can we prove such results, but that is in essence what's happening. So it is not laying all your eggs in one basket. It is pursuing multiple alternatives at once, and it's then gradually focusing the search where the most promise is. Whereas grid search is just brute force approach. You spread all your individuals as wide as possible and find something in there, and end up wasting a lot of time and also not necessarily finding the very best one because you are limited by the grid. So in that sense, that you could think of it as more intelligent version of that, much more intelligent. It's actually sometimes amazing how efficient it can be. So we've done at Sentient a couple of demonstrations in a multiplexer domain, which is a very easy domain to solve symbolically, but you can create it or turn it into a search problem. You have to find the right encoding of bits so that you get the right answers to any given address from your bit string. Now, the search space is huge in this case. It can be, and we've solved 70 bit multiplexer, which the search space is 2 to the 2 to the 70th. It's a very large search space, and still evolution can find solutions quite quickly. In hundreds of thousands or millions of trials, you'll find solution in that magnificently large space.
Can you take a step back and elaborate on that problem and how it's applied or how it's used in practice?
Right. Well, multiplexer it's a benchmark problem. It's not something that you would solve using evolutionary algorithm. It's only used to illustrate how or evaluate the different algorithms and how it works, how well they work. You have a number of address bits, and then you have a number of data bits. So that is your individual. And then what you are learning is rules, how to map those address bits to a data bit. And that's what the multiplexer does. Given an address, it gives you one of the data bits. So you can evolve it to solve that in various ways. You evolve rules, and the rules express that, okay, if we have this, and this bit in the addresses, then this is the output. So now the space that you're searching is the set of all rule sets. And that space is humongous, and we can calculate how large it is. This is work done by John Koza a long time ago, just to demonstrate how effective learning algorithms can be, evolutionary learning algorithms can be. At that time, I think we were considering 11 multiplexer, which has a search space of 10 to the, I think it's 616. And you can solve it by searching this sets of rules. And you, in the rules, you have a certain way of identifying the input bits and then ANDing and ORing them and so on, performing logical operations so that in the end you get the data bit. And you can calculate how large that search space is, how many ways there are to combine these input bits, address bits, and the logical operations on them. And therefore you can estimate how large the search space is and how hard the problem is. So in 11 case, it's 10 to the 616th. And we expanded it to 2 to the 2 to the 70th, and it still works. And that is, I think, to me, is very amazing that evolution can very quickly identify what actually works, those component solutions, those building blocks, and then put them together into a solution when the search space is huge. So that is power. But not everything is, of course, amenable to evolutionary computation. This happens to be the case.
Before we jump into that, you mentioned provability. Can you elaborate on the work that's been done there? For example, you mentioned in describing evolutionary algorithm that you kind of throw away the worst performing models or parameter sets, and then you mate, if that's the right word, the best performing ones. Is there formal proof that that's not susceptible to some local minima maxima, and you might get some better result by mating non-performers and performers?
Yeah, there's quite a bit of theory on evolutionary algorithms. It started already in the 70s with the schema theorem. And that says, the schema theorem states that in this process, the shorter the schemas are, the combinations of elements in the solution, in that bit string, in that genetic string, the shorter they are, and the more powerful they are, the more strongly they actually affect the fitness of the organism, then more prominent they will be in future generations. They will become more prevalent in the population. And that is a theoretical result. It's the schema theorem that shows that this happens in this mechanism.
How does a short schema apply to a practical problem? What does that mean?
Well, so a schema length means that you have, so let's think of genetic encoding, for instance, a string of weights on a neural network. So the schema means that a good neural network has this weight on this connection, this weight on this connection, and this weight on this connection. That's a schema of length 3.
Okay.
And it may be that indeed you have these kinds of interactions between weights in a neural network, and you have to set them right in order for the network to perform well. And the schema theorem just says that if there are short, small segments of weights or segments of the neural network that are powerful, they are easier to find. Now, if the schema covers a large number of weights, that's more difficult to find. Obviously, it makes sense, right? So you have to set more numbers correctly in order to see the benefit. And the schema theorem just says that if you have short schemas, easy ways of gaining the benefit, finding just 3 weights of the right values, that's going to be very easy to find, and it will very quickly become prominent in the population. And from the point of view of biology, that makes sense. I mean, if there are some genes that are very short, I mean, just single genes instead of interaction with multiple genes, that's going to be very prominent and very quickly propagate through the population. And that's the mathematics of schema theorem just expresses that idea.
Mm. And when we're training with evolutionary algorithms, is the schema length a constant, or does this method kind of zoom in and zoom out to different levels of resolution?
Yes, exactly. It will do that. We don't know ahead of time what the schemas are like. So we define the encoding. And you try to put in as much insight into that encoding as possible. You try to define a search space where you believe, first of all, that the solutions lie in that search space, and also that it's easy to move around in that search space. And that requires human thinking and creativity, but evolution will then find you the best combinations of those elements in that search space. But encoding matters. In some cases, it is obvious, and it's given by the domain very much. Like in neural networks, it's an obvious encoding to have weights put together into a string. But then when you think about it some more, you realize that, hey, actually the topology of the neural network matters as well. And then you want to have some way of encoding topology and letting evolution discover different topologies. And then you discover things like, well, if in order to make it easier to search this space, which now became much bigger because it's all the topologies in addition to just all the weight values, a clever idea is that let's start with a very small neural network, a small search space. Initially, we just start with neural networks that connect inputs directly to the outputs, no hidden nodes at all. And let evolution run in that space for a while, find good such simple networks. And then we'll add complexity. We add a hidden node and another hidden node, and then we add recurrent connections and gradually discover complexity as we go. And this principle, instead of starting with all kinds of topologies of neural networks as the initial population, if we start small, if we start simple and gradually complexify, evolution is much more powerful in finding these complex solutions. So that's what I meant by being smart about how you encode it and how you let evolution search the space. It makes a big difference. And this is one principle has turned out over and over again to be very useful.
How complex can you get with this technique? Like, if you come up with an encoding that can represent convolution layers and rectifying layers and the kinds of things that we do in, CNNs for computer vision, can this thing, come up with, a very deep model, the types of models that we're using for object recognition nowadays, or is it more limited?
Yes, it's a good question. So there's really been two approaches to doing this. And the first one I just described was that you have an encoding that in principle could encode anything, any kind of connectivity, and you build up from that. And that is actually very good on tasks like the reinforcement learning problem, where you have to define a custom kind of recurrency that retains just the right information over time in order for you to disambiguate the partially observable problem. But very recently, in the last 2 years or so, 2 years or so, another approach has emerged, and that's specifically to evolve deep learning architectures. And there's an interesting difference in that those architectures are composed of specific components. You mentioned, different convolutional neural networks, LSTM networks, dropout as a parameter, max pool layers, all kinds of structures now exist that people compose these deep learning architectures from. And it now makes sense to do this a little differently because we know that there are some components that are useful. Well, let's keep those components as a source material, raw material for evolution. And now you can come up with a mechanism that maybe operates in a couple of different levels. You could evolve the weights, you could evolve the components, and then you could evolve the overall topology that's based on those components. And this is currently where the deep learning neuroevolution is, evolving deep learning networks. There are multiple approaches, but by and large, they do this. They evolve the hyperparameters of those networks and maybe the topology of the networks. But then the weights are trained using a supervised training set like image recognition you mentioned. So there's still a big benefit from evolving those deep learning networks, even if you're applying it eventually to a supervised problem, because it's very hard to construct the right topology for your problem. Let's let evolution do that, and then use the training to set the weights. Weights, there are millions and billions of weights, but potentially it's very hard for evolution to get every single one right if it needs to do a mutation to get the weight value right. Deep learning is much better to doing that, but the topology matters as well, and the architecture of the components matters as well, and hyperparameters matter, and that we can optimize using evolution.
So help us understand. So what you just said was the evolution is better for the identifying the architectural solution, the connectivity and the types of layers and things like that. And traditional deep learning training techniques are better for the weights. Why exactly is that? You mentioned because there are a lot of weights, but I thought that was an advantage of the evolutionary approach.
Well, again, so it's actually a very simple point that if you are evolving the entire network, including the weights, then evolutionary operators need to set the weight values. And that means crossover or mutation. And mutation means that you are changing each weight randomly. And if you have a million weights, that's a very slow process. Mm-hmm. In contrast, something like deep learning or backpropagation, stochastic gradient descent, every time you show an example, you can change every single weight. So there's a lot more parallelism. It's a lot more efficient way of changing the weight.
So what we're saying here is if you've got training data, use traditional training techniques, gradient descent, which uses that training data to accelerate training.
Yeah, exactly.
And where you don't have training data is kind of at this higher level. Well, it seems like if you have the training data, you should also be able to use that for the architectural stuff. But I guess we don't have techniques for doing that like gradient descent. That's where evolutionary comes in.
Exactly. That's exactly the point. Yeah.
Okay.
Now, of course, people do research and try to break free of these restrictions. And you could, for instance, use evolution for the weights as well, even in deep learning networks. But there's an interesting approach that allows you to do it. And that is that you don't evolve every single weight separately, but you evolve, say, patterns of weights.
Coevolution?
Well, it's a different level of evolution. You could call it coevolution of different levels. Coevolution of topology, coevolution with components, and then weights. But the trick here is that instead of having to set each value independently using mutation crossover, you have some kind of a pattern that you are evolving. And then you use that pattern to derive the weight values. And in extreme, that pattern could be given by a different neural network, a separate neural network. So you are evolving a neural network whose outputs then give you the weight values. That technique is called compositional pattern producing neural net, and it's been used to evolve these deep learning architectures. And this is an example of how you can still use evolution even if you don't have supervised training data necessarily. You could still use a deep learning network with millions of weights, but you have to use this kind of an indirect encoding of its weights, perhaps through another neural network.
And so when you're using evolutionary algorithms to evolve the architecture and the connectivity of deep neural network, or anything for that matter, are you applying evolutionary algorithms hierarchically, or that as an approach hierarchically? Like, first evolve the connectivity and separately evolve the layers, or is it all done at once?
All of that is possible, and all of that is under research right now.
I guess I should have anticipated that.
Yes, exactly. And you mentioned coevolution. That's a powerful approach in evolution, and that means that you have two evolutionary processes, two or more, going on at once, and they interact. So in this case, it would be that you evolve the module that might be a convolutional layer or some other or LSTM type of a module, and then you evolve a topology, how you connect them together. And that means that you have two populations. One of them encodes a different LSTM node, and the other one encodes how they are connected. And then you can evolve them at the same time and evaluate them together as a single architecture, and then the individuals inherit the fitness of the entire architecture. And that's a very interesting approach. You could also do it differently if you have a way of assigning a fitness to, say, a single in LSTM node somehow, like maybe it's memory capacity or something. Then you could evolve that first and evolve a bunch of different, maybe LSTM nodes for different kinds of fitness functions. Use those as raw material at a higher level evolution and do it sequentially. That's also possible. But yeah, go ahead.
It almost suggests that there's probably some analog for GANs, generative adversarial networks, like generative adversarial evolutionary algorithms or something like that. Does that mean anything in this world?
Yes, exactly. And that's actually how GANs kind of got started and motivated.
Oh, really?
Yeah, so it was possible to evolve input examples that broke the deep learning network that had been trained very well in a training set. And then Jeff Clune evolved these patterns that were pretty much just noise, but the network still confidently claimed that, oh, that's a dog. And this is
like the school bus giraffe kind of example, that kind of thing?
I'm not familiar with that example. School bus giraffe, what is that?
I may be mixing up my objects and animals here, but there is some set of famous examples where, for whatever reason, if you give one of the same famous object detection CNNs a picture of a zebra or a giraffe or something like that, it confidently proclaims it to be a school bus.
Oh, I see. Yeah. There are many demonstrations of this same problem. That sounds like it's one of them. Yes. So you can mix the categories, but the most impressive demonstration to me is that there's an image that looks pretty much just noise. You cannot see anything in it, but still the deep learning system somehow declares that to be, I don't know, a school bus or something else.
Right.
But the origin of that was that it was possible to evolve those images. It wasn't just that we look at bad mistakes in a training set, but evolved these images that we had no constraints of what they had to be, and they turned out to be pretty much just noisy images. And evolution discovered that this is a way of getting the deep learning network to perform very poorly, classifying it confidently to something else. Yeah.
Oh, that's really interesting background. I didn't realize that.
And from there on, the whole field of generative adversarial network studied, like, how could we actually do this? How could we have an adversarial trainer or supervisor so that the network could actually perform better? Because you could use those images to train it as well as just break it. And this is a very close relation, and I think it's still being explored. It's possible to evolve training sets, and it's possible to evolve also these systems that are learning from them so that they become more robust, and also they develop internal representations that are more representative. So we can use evolution to bias these learning systems in a way we want. Make them more general, make them interpretable, and more robust.
Mm-hmm. Interesting. I interrupted you earlier when you were about to talk about classes of problems for which evolutionary algorithms are particularly suited and not suited.
Right. So there's, of course, a lot of work in trying to expand the space of possible problems. Now, we were comparing reinforcement learning with evolution. I would like to point out that reinforcement learning has a little bit different perspective and goal. The idea there is to model a learning of an individual more or less during its lifetime. So as it's living its life and it's performing, every step counts. And in essence, It's like an online method. The typical application of evolution is offline engineering type of application. That you do have a simulator, for instance, of the system you're trying to, or the environment for the system you're trying to evolve. And you can fail miserably in some of these candidates. The only thing that counts is that in the end you have a very well engineered system. And that is a different kind of a perspective. You don't get penalized for your exploration in evolutionary algorithms. You only get evaluated in the final result. Versus in reinforcement learning, it's a continual lifelong learning system, perhaps. Now, and that makes sense. I mean, evolution is an engineering approach, can be. We can evolve, for instance, controllers for finless rockets is one thing that we did. You couldn't possibly use it in a physical system because you would have to explode hundreds of thousands of rockets. But if you have a simulator for that system, you can do anything you want with it. You can explore very wild solutions. And as a matter of fact, some of those wild solutions developed into really good solutions in the end. And in the end, we have a controller for a finless rocket that keeps it stable in a reliable way. And that's the kind of typical application for for an evolutionary algorithm system. Now, on the other hand, if you have an online system that needs to learn online while it's performing, that's not as easy to use evolution for that. You have to build extra machinery for it. But you can. That's the kind of a reinforcement learning system that reinforcement learning initially came from. But it has also been to confuse everybody. It has been used to do engineering design as well, just like evolution is used to do online learning. But that's not that's opposite to the origin, and that's sort of the first application would be engineering versus online learning.
Mm-hmm. You mentioned simulation, and that reminded me of a question that I had earlier. Is there a relationship in, particularly in the context of the trading work that you've done, between Monte Carlo types of approaches, the evolutionary approaches?
Yeah, so Monte Carlo's simulation means just that you randomize your domain and generate new situations that way. Now, when you use it as a solution mechanism, you're banking on the idea that even randomized solutions are likely to be successful sometimes. So you could think of evolution as a 2.0 of that you actually trying to learn from your mistakes. You're trying to learn from those trials, and that is using crossover on the good candidates and mutation on the good candidates and focus the search more. And that is, I think, a good way to formulate the relationship. You could even look at some of the evolutionary algorithm methods. We've been talking about genetic algorithms, which is crossover mutation based. There are other evolution methods that are closer to something like Monte Carlo in that they will build a statistical model of the domain, which individual components, schemas, are, how reliable they are in predicting the fitness. You form that kind of probabilistic model of your search space. And then when you construct new individuals, when you construct offspring, you don't do it based on crossover and mutation, you do it statistically. You sample from that model. And it's still a population-based approach. In that sense, falls under the evolutionary algorithms, but it's closer to probabilistic reasoning and Monte Carlo methods and other statistical methods. And they perform quite well. Those methods perform quite well too.
Oh, interesting. Is there a simple way to kind of characterize the various types of evolutionary algorithms or approaches, or the various, tweaks that have evolved to the basic, generic approach?
Well, we can attempt to do it. Researchers are very creative. I mean, whenever you come up with a category, then they will cross the categories. And that's part of how research works too, that you will combine ideas across different approaches and categories. But genetic algorithms is one where the close connection to biology is obvious, crossover mutation. And then there are these statistics-based approaches, like I mentioned, sometimes called estimation or distribution algorithms, where you estimate the probabilistic model of what works and then sample from that. There are methods based on evolutionary strategy where you don't have crossover, but you have a small population and you're mostly using mutation to do the search, but you make the mutations intelligent. If you have a small population, you form, for instance, a covariance matrix of how your mutations co-vary. Try to find these interactions specifically, and then use that model of the interactions to construct new individuals. There's differential evolution. There's different buzzwords. I can give you a lot of these, but there's a large number of them, and they are based on sometimes letting go of the biological analogy and instead focusing on the idea that what if you do have a population? How could you utilize the information in that population to construct new individuals better? And that is kind of the general umbrella of evolutionary algorithms. And you could even think of an interesting direction trying to go towards the biology, going the opposite direction. I'm talking about abstracting it to probabilistic reasoning, probabilistic and stochastic search. But you could also go towards biology. And there's an interesting idea. Try to take some ideas that are more biological, for instance, indirect encoding. The fact that in biology, DNA, the actual ribonucleic acid, does not really specify the full individual. There's a large network of interactions that come after generating the proteins from the DNA and RNA. So genetic regulatory networks are a huge part of biological construction from the DNA to an individual. And currently we are pretty much missing that in these algorithms. So there's a lot of complexity in this kind of indirect encoding. There are approaches that try to invoke genetic regulatory networks. There are approaches that are trying to include a developmental phase, which is also big in biology. So after the individual is constructed, after it's born, there's usually a period of learning that happens, interaction with the environment, and that then constructs the final individual. For instance, human brain, we have 30,000 genes maybe in the genome. There's no way the brain can be specified except at a coarse kind of instructive level, pattern level. Most of the brain structure is actually learned in an interaction with the environment. Evolution just produces a starting point for that learning. So combining learning and evolution that way is fundamentally biological, and it's also something that we should be looking into, and we are looking into, people are looking into it.
Wow. This is really a fascinating area. For folks that want to dig in a little bit deeper or learn more, where is the best place to start? Are there canonical papers they should start at? Is there a resource that you like to recommend people take a look at?
Sure. There are some classic books that are about evolutionary algorithms, and you can find genetic algorithm evolutionary computation books that are textbooks. Holland, Mitchell, Goldberg, for instance, they tend to be a little bit old right now because the field is developing very rapidly. There's been explosive growth. But the typical sources on Scholapedia, for instance, and then the tutorials that appear in the main conferences, I think would be a great source. There will be actually a Genetic and Evolutionary Computation Conference, GECCO, starts tomorrow, as a matter of fact, in Berlin.
Oh, wow.
And the first 2 days are tutorials. And lots of those tutorials are online, even some of the videos about the tutorials online. And I think that those are really a great way to get started. It is a big field and in a very diverse field. It's kind of interesting because evolution drives on diversity. The algorithms drive on diversity, but the field is also tremendously diverse. So that is a bit of a challenge, that you may get lost in all this terminology and all the different approaches. And that's why I'm recommending that maybe starting from one of the textbooks, even if it's a little bit older, is a good idea that gives you the perspective. And then looking at the tutorials, and maybe there on it's you should have access to a lot of literature on the internet.
Are there tools and frameworks, or do the deep learning frameworks, the TensorFlows of the world and the like, do they have any kind of support for evolutionary algorithms, or are folks rolling their own?
Yeah, so there's support. TensorFlow, I don't think currently has evolution component, but it is likely that it will in the future. It's an open source project and people are contributing to it, so it's very likely to happen. There's, for instance, ECJ, Evolutionary Computation in Java. That's a big effort, George Mason University, and that software includes many different evolutionary algorithms, and that I think is currently the best source to get started with, software system to get started with. Yeah.
Great. Well, to wrap things up, can you let folks know what's the best way to check in on you or to get in touch with you?
Well, I have a name that's very easy to find if you spell it correctly.
If you can figure out the spelling.
Yeah, so I have a website at UT Austin where much of my research from my whole career is always there. I try to keep that up to speed. And of course, Sentient itself has a set of blog posts and web pages describing the technology we are developing here, which is evolutionary computation and deep learning. So those sites are usually quite well up to date. And then we have pointers to more material that you can use those as a starting point.
Okay, great. And we'll link to both of those in the show notes.
Very good. Thank you.
All right. Well, Risto, thank you very much. This was amazing.
Yeah, it was a lot of fun.
All right, everyone. That's our show for today. Thanks so much for listening, and of course, for your ongoing feedback and support. For the notes for this episode, head on over to twimlai.com/talk/47. I've got a quick favor to ask. If you enjoy the podcast, and especially if you like this episode, please take a moment to jump on over to iTunes and leave us a 5-star review. We love to read these, and it lets others know that the podcast is worth tuning into. Another thanks to this week's sponsor, Cloudera. For more information on their data science workbench or to schedule your demo and get a drone, visit twimlai.com/Cloudera. I'd also like to send a huge shout out to friend of the show, Hillary Mason, whose company Fast Forward Labs was acquired by Cloudera just last week. For more on Hillary and Fast Forward Labs, check out my interview with her at twimlai.com/talk/11 and my interview with the former president of that company, Catherine Hume, at twimlai.com/talk/20. Thanks again for listening, and catch you next time.